Hello everyone, my name is Sho from Japan. Today I am going to share a theoretical concept that explains how life might arise from non-living matter. We live in a world teeming with life. Approximately 6,000 species of mammals, about 1 million species of insects, around 300,000 species of plants. And when including other groups, the total number of species on Earth is estimated to be between 5 to 30 million. One common characteristic of all life is our ability to reproduce ourselves, which is made possible by our genes. By analyzing genes and tracing back the evolutionary tree, we reach our common ancestor, known as LUCA, last universal common ancestor. This raises a fundamental question. Where did this first life come from? Let's see what mainstream science has achieved so far in answering this question. In 1953, a groundbreaking experiment was conducted at the University of Chicago. The research team placed hydrogen, methane, ammonia, and water vapor inside a flask and applied electrical discharge. These molecules were believed to be major components of the primitive atmosphere. This experiment led to the production of amino acid, suggesting that lightning striking the primitive atmosphere could generate the building blocks of life on Earth. Other hypotheses propose that life originated from space. This idea is supported by reports indicating that life-related elements, such as adenine and guanine, have been found in meteorites. Recent researches suggest that life may have emerged from hydrothermal vents in the deep ocean. Until 1970, the deep ocean was considered a lifeless desert. However, a survey discovered numerous sea creatures living near these vents, forming thriving ecosystems. This discovery sparked significant interest and further studies. It is believed that the structure of some vents is conducive to the emergence of life. This view aligns with results from genetic analysis, which suggests that our common ancestor lived in a high-temperature environment. Thus, hydrothermal vents are strong candidates for where our ancestors lived and originated. Despite these findings, much more research is needed to provide a concrete answer about the origin of life. However, our question may not require such a definitive answer. Intuitively, we perceive life and non-living matter as fundamentally different. It seems counterintuitive to suggest that life arises from matter. Therefore, we can ask, is there a satisfactory explanation to bridge this conceptual gap? And what mechanism, if any, allows nature to create life from non-living matter? Today, the concept of evolution is familiar to many people. Throughout history, genes have mutated randomly as our ancestors reproduced. Some mutations became extinct, while others survived to become us and other living organisms present today. We can see that randomness is a driving force behind evolution. Without randomness, our ancestors would remain unchanged from billions of years ago, and there would be no diversity of life. So, is randomness also the driving force behind the emergence of life? In other words, did the elements of life assemble randomly to form life? In 1987, a book titled Origins, A Skeptic's Guide to the Creation of Life on Earth, was published. The book calculates the probability that life arose spontaneously by chance. The result indicates that the probability of a random assembly of molecules forming simple life is approximately 10 to the minus 40,000. This is akin to having about 40,000 zeros after the decimal point before reaching 1. How small is this number? We are familiar with astronomical numbers being huge. Can we counterbalance the tiny magnitude of this probability by multiplying it with astronomical numbers? Let's explore this idea. Firstly, we know that galaxies are enormous. The diameter of our Milky Way galaxy is about 100,000 light-years. If we convert this to meters or feet, it's roughly 10 to the power of 21 meters or 10 to the power of 22 feet. Multiplying this by 10 to the minus 40 thousands gives us approximately 10 to the minus 39.98 thousands. Although this is a significant change, it feels almost negligible. What if we multiply it by the number of stars? The total number of stars in the universe is estimated to be around 10 to the power of 23. As we've seen before, the result is still not sufficient. Let's imagine the largest number in the universe. We know that atoms are extremely small, and our bodies, Earth, and solar system are composed of an immense number of atoms. What about the total number of atoms in the universe? Current estimates suggest there are around 10 to the power of 80 atoms. This number is much larger than the previous two. To reach this number, we would need to multiply the number of stars by about 1,000,000,005 to 6 times. However, as you already know, it's still insufficient to counterbalance the smallness of 10 to the minus 40,000. The probability that life arose by chance is so small that nothing in our universe is of similar magnitude. However, we also know that there could have been a myriad of molecular assembly trials throughout Earth's long history. According to the book, the number of trials is calculated to be about 10 to the power of 51. This is still not enough for life to arise by chance. If the accidental emergence of life is so difficult, one might think that perhaps it was created by a divine being. Such sentiments are understandable, but we do not take that stance here. Instead, life can arise spontaneously from chemicals through mechanisms distinct from mere chance. In his book At Home in the Universe, Stuart Kauffman proposes a theoretical framework to describe the emergence of self-reproducing systems, such as life. He argues that the order of the biological world is not merely tinkered, but arises naturally and spontaneously. This perspective suggests that, with a sufficiently diverse mix of chemicals, life may arise spontaneously, because diversity triggers sequential reactions that can lead to self-reproduction. Let's explore how sequential reactions arise from a diverse mix of chemicals, and how these reactions become self-reproducing systems. Let's consider a mixture of chemicals. Reactions may or may not occur within this mixture. Suppose a random pair of chemicals in the mixture reacts with a probability of p. We want to determine how likely reactions are to happen in the mixture. If the mixture consists of 3 species of chemicals, the probability of A reacting with B is p. Similarly, the pair BC reacts with probability p, and the reaction between AC also occurs with probability p. By summing up all combinations, the total probability of any reaction happening in the mixture is 3p. If the mixture is composed of 4 components, we have combinations of AB, AC, AD, BC, BD, and CD. Therefore, the total probability is 6p. For a mixture of 5 species of chemicals, the probability is 10p. With 6 species, the probability is 15p. For 7 species, it is 21p. Finally, if the mixture consists of n species of chemicals, the probability is n times n minus 1 times p divided by 2. We observe that the probability grows in the order of n squared. This means that even if p is tiny, the diversity of chemicals can overcome the threshold, and reactions will occur in the mixture. Next, let's consider what happens when we further increase diversity after reaching this threshold. This results in reactions occurring in multiple pairs of chemicals. The compounds produced will trigger other reactions, ultimately leading to sequential reactions happening in the mixture. Now, let's explore how self-reproducing systems can arise from sequential reactions. Suppose we have a diverse mix of chemicals which we'll call X. We'll add new chemicals to X one by one to see if they react with X and produce new chemical compounds. For the sake of clarity, we won't draw X anymore, but imagine it's present everywhere in the background. First, we add A, but it doesn't react with X, so the mixture remains unchanged. Next, we add B and C, and still no reactions occur. Now we add D. D reacts with X to produce J, but since J doesn't react further, we move on. We then add E, which reacts with X to produce L. Next, we add F, and it reacts with X to produce E. Immediately, E reacts with X to produce L again. We add H and G, but no reactions happen. Then we add I. I reacts with X to produce F, which in turn produces E and L. Finally, we add K, which doesn't react itself, but acts as a catalyst for L to produce 2I. These 2I produce 2 Fs, E, L, and ultimately 4I. We can see a self-reproducing loop of reactions emerge. Of course, real-life biological systems are far more complex than this self-reproducing system. However, we can imagine that many different kinds of loops might emerge from this complex world. Perhaps one of these loops is mediated by a primitive form of RNA or DNA and evolved to become life. In this video, we've explored the possibility of life emerging from non-living matter. If we assume a random assembly of materials, it's nearly impossible to expect life to arise from matter on Earth. However, by considering a diverse mixture of chemicals, we've seen how a self-reproducing system can form spontaneously. Our home, Earth, is largely covered by water, which allows the chemicals to dissolve and interact with each other. It is widely believed that the ocean is the origin of life. The ocean, with its varied chemical mixtures, could have given rise to self-reproducing systems and ultimately, life. Thank you for watching, and hope you enjoyed the video. Please click the subscribe button, and I'll see you in the next video.